This is an exercise to illustrate to you how to apply mathematical induction. Mathematical induction works like domino effect. Imagine you have a few domino lying up. Let Pn be the statement. The n domino falls backward. Then we try to prove two statements. A. P1 is true. That means the first domino fall backwards. Then second statement. Pk is true implies Pk plus 1 is true. That means if the k domino fall backwards, then the k plus 1 domino fall backwards. Then we can conclude that Pn is true for every n. The principle of mathematical induction says that if Pn be a predicate defined for integers n, suppose the following statements are true. Basic step. Pa is true for some fixed a belong to integer. The inductive step. For all integers k greater than or equal to a, if pk is true, then pk plus 1 is true. The conclusion is, for all integer n greater than or equal to a now, p of n is true now. Let's see how do we apply mathematical induction to show that 1 cube plus 2 cube plus 3 cube plus all the way to n cube go to n times n plus 1 divided by 2 then square it. For all n belong to z plus. Now the z plus is a symbol to indicate positive integer. Means you start from 1, 2, 3, 4, 5, and so on. The symbol there means this is an element of, it actually means belong to. The solution will look like this. First, you let Pn equal to 1 cube plus 2 cube plus 3 cube all the way to n cube equal to n times n plus 1 over 2 square. Then, step number 1 is to prove that P1 is true. What does it mean by P1 is true? The left-hand side of P1 is 1 to the power 3. So, we can write left-hand side of P1 is 1 cube. The right-hand side of P1 is when you put n equal to 1 inside. The right-hand side, you get 1 times 1 plus 1 over 2, then square. Then what is it equal to? Is 2 over 2 square is also 1 by putting n equal to 1. Into the right hand side. Now you find that the left hand side of P1 is 1 cube, which is 1. The right hand side of P1 also 1. They are equal. So we have proved that P of 1 is true. Step 2. Assume Pk is true for all k belong to the set of positive integer. So what does it mean by Pk? So you replace m by k in Pn. Then you get the statement 1 cube plus 2 cube plus 3 cube all the way to k cube is equal to k times k plus 1 over 2 then square. Step 3. Prove that p of k plus 1 is true based on pk is true. First, what is p of k plus 1? You replace m by k plus 1 in Pn to get p of k plus 1 statement 1 cube plus 2 cube plus 3 cube all the way to k cube plus k plus 1 cube is equal to k plus 1 times k plus 2 divided by 2 then square. This is exactly obtained by Pn by changing n to k plus 1. How do you prove that this is true? You have to show the left-hand side of pk plus 1 is equal to right-hand side of pk plus 1. Let's look at the left-hand side of pk plus 1, which is 1 cube plus 2 cube plus 3 cube all the way to k cube plus k plus 1q. Now, my sum of first n term is given by the assumption that this is equal to k times k plus 1 over 2 square plus k plus 1q. So the sum of the first k term is this. Based on pk, we can see this here. pk, say this. So we have copied the result of pk to here. Then we expand it. So let's see what is the sum look like. Can we simplify the sum? So this is k squared, k plus 1 squared over 4 plus k plus 1 cubed. Then we must know how to sum. So when you want to sum up these two terms, you have to find a common denominator, which is 4 now. So k squared, k plus 1 squared over 4 plus 4 times k plus 1 cubed over 4. Now they have the same denominator. You can add them up over 4 k squared, k plus 1 squared plus 4 k plus 1 cubed. Notice that k plus 1 squared is a common factor. So you can factor out a k plus 1 squared and left with k squared plus 4 times k plus 1 after you pull out a k plus 1 squared over 4. Now simplify some more. K plus 1 squared, k squared plus 4 times k plus 1, you get 4k plus 4 over 4. Now k squared plus 4k plus 4 is a perfect square, which is k plus 1 squared times k plus 2 squared now. Since this is a perfect square, k squared plus 4k plus 4 perfect square. And again, the term is a perfect square again. This is k plus 1, k plus 2, divided by 2, then square again. And you have this, the right hand side of pk plus 1, because the right hand side of pk plus 1 is exactly this. Let's go back and check. The right hand side of pk plus 1 is this term, k plus 1, k plus 2 divided by 2 square, right? So we have to prove that, the left hand side of pk plus 1 all the way until we reach here and get the right hand side of pk plus 1 now. So we have proved that pk plus 1 is true whenever pk is true. And since we also prove p1 is true by mathematical induction, Pn is true for all n beyond the positive integer. That's the end of the proof.